We'll start with the next talk. We have Preethi here to give a talk on geometry of efficient fine-tuning, low-rank adaptation, intrinsic dimensions, and subspace learning. So can we have a huge round of applause for Preethi?
Hey, so hi, I'm Preethi. I'm from Sahaj Software. Today we'll be talking about why PEFT works so well, because PEFT is a most sorted after fine-tuning technique today. PEFT stands for parameter efficient fine-tuning technique. One of the PEFT techniques is LoRA, low-rank adaptation. And there are multiple types of PEFT, of which adapter-based PEFT took off very well, as in they are the go-to algorithms to fine-tune large models today. So there is a fundamental reason why it works very well. Most people know how how LoRA works, or how most of the other PEFT algorithm works, but today we'll delve into why it works the way it works and why it works so well, right? So in the process, we'll also look at what is subspace training and so on, right? So yeah. So if this were your neural network, imagine, which has about 10 layers, then conventionally the way people used to fine-tune earlier is to freeze most of the earlier layers and only fine-tune the last layer, right? The green ones. Most of the red ones are frozen. So so in the process of training, for a particular downstreaming task, as in this pre-trained model is already trained on a large amount of data, you use that knowledge, you train this model, only the last layer or the last few layers, for your specific downstreaming task with your domain data. That's basically fine-tuning, right? If you were to transport this, or apply this technique to today's era of large models, say Llama 3.18 billion, which actually doesn't even qualify as large model anymore, has about 32 layers, right? And the last layer has about 218 million parameters. So typically to train any layer, you need, if you have X number of parameters, you typically need around 3x to 4x amount of space, because you will need to store every weight's gradient, movements, etc. Right? So the resource requirement for training just one layer of a Llama 3.18 billion is pretty massive, right? So as you can see, it's about 218 into 10 parsecs, which is because it's so many million, 4 bytes per parameter, right? And let's say if it's 3x, it's quite heavy, it's quite expensive. So that's when adapter-based PEFT evolved. So the idea of adapter-based PEFT is you have a base model that is fully frozen, completely, all the layers are frozen, but you will introduce a few modules, layers, into the base model in some fashion, without getting into details, which are called adapters. So only these are going to be modified during the training process. So the idea is they will be introduced in such a way that you can plug it out if you want to save them. So you don't have to save the entire model, just save the adapter for every downstreaming task. If you have 10 downstreaming tasks, you have 10 small adapters, right? But one of the key things about using adapters is that it has to be smaller in size compared to the base model layers, because otherwise the whole point is lost. The initial point is lost, right? So the question today we are going to dwell is, how are fewer parameters even enough for fine-tuning? Now, how did this idea even get inspired? Like, where did this come from? So this LoRA paper has this line, right? Learned over parameterized models in fact reside in a low intrinsic dimension. Let's try to understand this line, right? To understand this line fully, let's quickly go through the training process. So we'll answer some fundamental questions, which will take us to a point where understanding that line becomes easy. Consuming that line becomes easy. So what's a model dimension? Suppose if this were your 2-layer network, you have W1, W2, 3, 4, 5, 6, 7, 8, about 8 weights and 4 biases. All of these are learnable during the process. Your X1 and X2 are your inputs. A very simple layer, right? So the 12 parameters that are basically learnable, that N, that's your model dimension, typical convention, okay? So these inputs go via your network, and your network is basically, if you were to mathematically formulate it, it will become a nonlinear function. You can put the entire thing in one function, right? and then you get some scalar value out depending on what the loss is. So overall it becomes a cost function or objective function or whatever people call it, and then you keep iterating it over the entire data set to find the best case W's and biases so that your loss is minimal, right? So quickly, if your input data is x1 and x2, your network architecture is basically a function of your inputs and your learnable variables. Your objective function or loss function or cost function, so many names to it, is basically another function wrapping on your model network architecture, right? This takes care of some way comparing your predicted value and your ground truth value. So this C is also a function. Now objective landscape is the shape that the C takes. So if this were your task that you want to accomplish, the task is basically a function mathematically, and that will take some shape. So that's called the loss landscape. So the training is basically you're navigating in that loss landscape to find a point where your loss is minimal, right? This is what training process is. So once your input data, your network architecture, and your loss function is fixed, your landscape is fixed. There is, in that fixed landscape, in that fixed shape, which people usually imagine as hills and valleys and portrait, that makes sense only within the 3 dimensions. I think beyond that, we don't know how it looks like, and hills and valleys is no more true or accurate, right? That's a side fact. But yeah, so once these 3 things are, the first 3 things are fixed, your landscape is fixed. So you're just navigating in the landscape to find a point where your loss is minimal, right? So let's try to answer what is intrinsic dimension, right? If n were your total number of parameters, in this specific case, let's say you have 3 parameters in your model, x, y, and z, assuming these are w1, w2, and w3, okay? Your zero cost points, or you want to reach this particular point where your loss is 0, right? Effectively, you have to traverse in these 2 directions, x and z directions, in your loss function, in your loss landscape, to hit this point. But once you have reached this point, given this particular landscape, no matter where you go in this y dimension, you will remain in 0 cost. Does it make sense? Because the way the function looks like, given this function is already there, once you have hit one of the 0 cost points, no matter where you travel in that y dimension, you will remain in 0 cost, right? So effectively, you're using only 2 directions to travel. So the 2 directions are actually doing the effective learning in your training process. So that 2 is basically your intrinsic dimension of your task, right? So the total number of parameters basically amounts to your intrinsic dimension plus the leftover solution space. Now this will make sense in a larger example where your n is running into millions of parameters. In this specific case, let's say you have a simple 3-layered MLP, 784 cross 200, 200 cross 200, and 200 cross 10, and you're performing a MNIST classification, 10 class classification task. You're dealing with about 2 lakh parameters, right? Of which, suppose if you were to learn using all the 2 lakh parameters, if you're going to hit the best case performance, let's say your 90% performance, what is that number of parameters that you will have to learn so that you will hit 90% of your best case performance? As in, if you just fine tune 750 dimensions, 750 parameters, 750 directions in your objective task, you'll be able to hit 81% performance. So that is represented by D90, okay? So effectively, when I say D90 is 750 parameters for this task, all I'm saying is just by modifying 750 directions, 750 dimensions, learning 750 parameters, keeping everything else frozen, I can hit 90% of the best case scenario, all right? So the rest of the dimensions will add to your solution space. Now what does that mean, right? So if this intrinsic dimension of any of most of these objective landscapes, most of these tasks is so low, then why are your networks so large, right? That's the next fundamental question. So this solution space basically adds to the number of ways in which you can reach your zero cost solution. This image is kind of an analogy. If you were to reach the valley, there are many ways to reach the valley. If you're saying you have only 750 directions to reach your zero cost solution, versus if you're saying 2 lakh minus 750 ways to reach one of your zero cost solution or reach anywhere in that space, in that solution space, you'll still remain in zero cost. That's a great way to train. So basically your convergence is faster. Otherwise, if you're saying there's only one way to reach, the convergence will probably take infinite time, right? So that's essentially why our networks are so large, because of the training convergence, not because all your parameters are participating in the learning activity, okay? So the next obvious question is, how do you extract the 750 from those 2 lakh parameters, right? The answer is you don't. So instead, first of all, it's practically very difficult to, theoretically you can come up with ways of saying, I will keep noticing how much each of these parameters are learning in every iteration and then choose the best of them. But it's practically very hard to implement, because with every data set, different parameters will learn different things. So it's very hard to distill that and say, I'm going to pick these particular 750 of them. So what people instead do is, they project the base model parameters, that is n, into a lower dimension subspace. And they try with different numbers. Let's say you start with a ID of 10, 20, 30, you reach 750. And that's when, if you hit like, we already discussed, right? If you're hitting a D90 at 750 parameters, then you will declare that for this particular task, my ID is 750, right? Rest of all the parameters are your solution space. So the next question is, how do you measure this ID? While we spoke in English, what actually happens is, so you first have to, there's an associated code. I will link it to the code in the end of the talk. So you first freeze the base model parameters. In our earlier example, we already said we will have a 3-layered MLP. Each first layer is 784 cross 200, second layer is 200 cross 200, third layer is 200 cross 10, right? You first freeze them. The red arrows are for freezing. These weights are there, but you're not going to modify them during the training process, right? Next bit is, you will create the intrinsic dimension parameters, which is this green box. Those are the only 750 parameters you're going to modify during the training process. And there should be a way for you to project this n down to 750, right? This 2 lakh down to 750. That's where your projection matrices are going to play a role. So each of these projection matrices are designed in such a way that you can project for a layer 1, let's say, your layer 1 size is 784 cross 200. You flatten it, that becomes about 156,000. Your projection matrix size will be 156,000 into 750. So when you do a matrix multiplication, you will end up with a 750 vector. And this is the only vector that you're going to change during the training process. Everything else is frozen. This is just a constant matrix. This P projection matrix is just a constant matrix. And you're not going to change these red arrows in the process of your fine-tuning or training. Only the green arrows will get changed, right? So some PyTorch related questions, right? So this intrinsic dimension, you're going to initialize them as NN dot parameters. If you're all familiar with PyTorch and how you initialize these layers and modules, etc., there is a fashion in which you will initialize this base model. There is a fashion in which you will initialize these extra intrinsic dimension parameters, right? If you want some, because there is a notion of a computational graph where the moment you have a model, PyTorch has a sense of how to flow through this network to do a forward pass and a backward pass. So now you have disjoint elements. You have to connect them in a fashion where your PyTorch will understand how to do a forward and a backward pass, right? So intrinsic dimension is initialized as NN dot parameters, right? And these projection matrices are initialized as buffers, register buffers. So what's the difference between NN dot parameters and registered buffer is the following. NN dot parameter is basically a tensor. Usually it holds learnable weights, learnable biases, etc. That's what you use it for. Buffers are used for storing masks, projection matrices, which are used in the forward pass, which are used in the computation, but their values don't get changed. As in, there is no gradient associated with these with buffers. There is a gradient associated with parameters, tensors, but there is no gradient associated. They're not tracked by the optimizer, right? So, but the tensors are tracked by your optimizer while training. So there's a state dictionary available for both of them, but there is a fundamental difference between how they operate, right? So theoretically, you can have all the frozen weights initialized as buffers. You can have intrinsic dimension also initialized as, as part of your base model, etc. All of this is possible, but implementation gets really tricky because each of them practically has some use case. And for instance, if you want to, this intrinsic parameters, which are modified, right, during the training process, why can't that be part of your base model? Say gradient torch grad is false for your base model, but keep the intrinsic dimensions gradient to be true, and it can be technically part of your base model. But the way the subspace training is designed, the way subspace training works, one single intrinsic parameter vector is used by multiple layers. So it's hard to introduce them into the base model, right? And because to have the possibility of experimenting with multiple IDs, having this as a separate piece, but also part of the computational graph helps, right? This is a provision which PyTorch gives you. And that provision has led to, which one leads to, random subspace training leads to the provision in PyTorch or the other way around, we do not exactly know, but that provision is basically led to most of the innovations, right? So it's good to appreciate that. So let's look at the training process. Effectively, we are going through the computational graph now. We will see how forward pass happens. So these projection matrices for every layer, because you know the layer dimension already, the projection matrices size is going to be dictated by the layer dimension, right? That's what you will first initialize. Then you will multiply this projection matrix with your intrinsic dimension vector. All of these are carrying some values, right? So the way matrix multiplication works, you will compute, or the output will be of the size of 784 cross 200. So basically, let's go through in detail of one layer. So if your projection matrix is of the size 156,000 into 750, and you do a matmul with 750 cross 1, you will end up with a 156,000 vector, which you can reshape back into your original layers shape, which is 784 cross 200. So these values, whatever you got, you will just copy them in your model. So when you're doing a forward pass, you will work with these new values, right? So 1, 2, and 3, and then your input goes via layer 1, layer 2, layer 3, and then while coming back during the backward prob, you will not modify any of these weights. You will reach the intrinsic dimension via the matmul and only modify these intrinsic dimension weights. And you will not touch any of them. And this process repeats, right? This is how the computational forward and backward pass flows in your computational graph. This is a more figurative way of representing the computational graph than just, arrow marks. So I thought the animation might not be very clear, so this picture is a lot more intact. Yeah, so now if we try to revise the line that we started on with, learned over parameterized model in fact resides in a low intrinsic dimension. It means that while the model is highly over parameterized, while we have about 2 lakh parameters, the effective learning is happening in only intrinsic dimension, right? So if you try with intrinsic dimension of size 10, you were hitting a D9, the best accuracy that you could get is 19%. So I tried to reproduce the paper which proposed this idea, and as they said, around 750, you hit a D90 of 90%, right? So now can we look at this fine tuning in the lens of intrinsic dimension? What does it mean? How is this lead to fine tuning becoming easier, right? So they observed that when larger the models, when the n is really, really large, it's easier to fine tune, which means the models which have very large number of parameters, their D90 was much less for a given fine tuning task. And models that undergo longer pre-training, also they found that their D90 was quite low for a given fine tuning task, and vice versa for models that are smaller, right? The paper references are given below. Now, coming back to the original idea, one of the original slides where we said adapter-based PEFT means introducing adapter layers into your base model, which are smaller in size, and only modifying them during the fine-tuning process. So this subspace training which we looked at earlier, right, the forward and the backward, that itself is basically fine tuning. But the novelty lies in how are you having these, in the simplest case, we saw that the intrinsic dimension was a simple vector of size 750 cross 1. Novelty of algorithms lies in designing those adapters. So that vector that you saw there, if you were to imagine it as an adapter, or at least the adapter based PEFT guys looked at it as an adapter and tried to come up with more and more efficient algorithms, efficient designs to be able to make the computation and memory efficient during the process of fine tuning, right? So small detour, we will be able to appreciate how the practical significance of what we learned as part of theory, we'll be able to appreciate if we understand LoRA. We'll try to get the superficial understanding of how LoRA works, right? So for that, recap of matrix decomposition. Suppose if you have a matrix of size 200 cross 2000, let's say 4 lakh parameters. If you are able to decompose them into two low rank matrices of size say 200 cross 3 and 3 cross 2000, if you multiply them back with the way of how matmul works, you will get the 4 lakh parameters back, right? This is a simple recap. But you have to observe that 4 lakh parameters is way, way larger than 6600. It's about 60x safe, right? Now this is the idea behind LoRA, where they said, if your original matrix was, let's say, size A, or the same size that we saw earlier, 200 cross 2000, if there is some way, people must be familiar with SVD, singular value decomposition in school. So if you give a rank and if you give a matrix, it will decompose it into two smaller matrices, such that if you multiply those two smaller matrices back, you will get approximately the original matrix. So this idea is used as data compression in almost all kinds of engineering applications, right? So if you, in the source, if you, instead of sending the matrix A as data, you would rather send two small matrices and have the guys in the destination multiply them and get approximately the original matrix back. So that's one way how data compression works. So the authors of LoRA said, why not learn this B and C for a given downstreaming task? Instead of having an adapter matrix with full rank, let's go even further low. Let's say instead of having a full rank adapter matrix, let's have it decomposed into two smaller low rank matrices and have them initialize them in some fashion. Again, the details of initialization is another ballgame, but initialize them in some fashion and train them for the downstreaming task. Keep the base model frozen. So if this were your base model, assume this is your MLP that we discussed. This is a different way of representing a matrix, a layer. This was your first layer, second layer, and third layer. And if you chose to adapt the first and the second layer, instead of having, we started off saying that adapter layers have to be very small. Instead of having a matrix, a full rank matrix, let's have two low rank matrices, right? And without getting into details of how LoRA works, the idea is that this adapter gets plugged into your base model. You use it for your downstreaming training or inference or whatever it is. When you don't need it, just plug it out and save it somewhere else, like save it in a hub. Now, tomorrow, if you wanted to perform inference on a particular downstreaming task, you download the base model, get the whatever yellow blob you want from hub, plug it back, use it for inference. So if your base model size of 3 layered in this example, which had about, which was at the size of, say, let's say 1700 KB, then your adapter size will be as small as 51 KB if you were to use rank 3, right? So effectively what we are trying to say is the adapter-based PEFT has made the whole fine-tuning process pretty efficient in terms of storage, because we started off saying if I were to use the conventional technique of fine-tuning on Llama 3.1, I would end up training 218 million parameters. Instead, if I were to use adapter-based PEFT with rank as small as 2, then I would end up only having 5 million I would end up having to train only 5 million parameters, which is pretty compute efficient, right? So this is the physical application of the theory of intrinsic dimension that we learned. So that idea led to adapters, having smaller parameters enough to fine tune, etc. Right? So the idea is you just have smaller adapters for various tasks, but you have a single large model that you can plug in and plug out whenever you want. So yeah, so this idea basically is from a paper called Measuring Intrinsic Dimension on Objective Landscape, which got published in 2018. It's pretty math heavy and ML heavy. Uh, it's basically hard to understand. Yeah, but cut to 2024, I was able to reproduce the paper in a couple of weeks by having somewhat understanding of math and ML. Probably today people can do it in a couple of days. So yeah, I wouldn't have been able to learn all of this without generative AI and coding agents. Yeah, thank you. This is the link to the code, the blogs. There are 4 blogs, 2 of them on how LoRa works, 2 of them on why it works the way it works. Thank you.
Thank you so much for the talk. Are there any questions that you wish to ask? You can use that mic. Yes.
Hey, that was a very fun talk. I loved the slides, and yeah, this was very entertaining and informing. I'm curious to know what coding tools did you use, especially because in matrix multiplication, it like oftentimes outputs code that looks very correct, but then the small intricate matrix multiplications don't end up working out like absolutely correctly. And so I'm curious, what kind of coding tools did you use, and how did you like think about the matrix multiplication in maths first, and then somehow ask the agent to then translate it into code, or like what was your process like?
The paper had some information about how to use random projections, why random projections work, if not random projections, what other projections work, and etc. So when I started off, I didn't know enough about how training hooks in PyTorch and all work. But for instance, I'm only used to using model directly. So how do you inject a separate set of parameters like NN parameters, etc. So if you ask the right questions, it mostly gives the right answer. So basically, if you tell things like, I have a base model, I have a notion of intrinsic dimension, I need something to get the base model projected into the intrinsic dimension, it completes the story.
Nice, very cool. Yeah. And did you use like Cursor or Claude Code? Like, what's your favorite tool?
In this, I worked at that time. Claude Code was not there. ChatGPT and Claude normally, yeah.
Nice, very cool.
Probably if you were to do this now, I think you can do it much faster. Yeah.
Nice.
The paper didn't come with the code, so had to reproduce it to understand if it really works.
Yeah, it's pretty cool that you can reproduce.
Yeah, and that was one of the foundational papers that led to all the works later, including LoRa, etc. Yeah.
Thank you.
Yeah, thanks.
So yeah, thank you for the great session. I have 2 main questions, ma'am. First is, when you said that we do not update the actual weights,
Yeah.
those are all frozen. We just update the intrinsic dimensions, right? Using by multiplying the projection. We take the projection matrices, which are also fixed. What we initially randomly initialize the intrinsic dimensions. We through that we generate the tensor with the same size as of the original weights, right?
Correct.
And this is how we train.
Yeah.
So while training, the output with the updating intrinsic dimensions, the output is also changing, which we then put to the original model, right?
Copy, yes.
Yes. So this is not how, isn't that updated then? How we call them frozen then? If those are really overwritten?
No, the grade, okay, when you mean update, you're saying the updates are aligned to reduce the loss. That job is done by the intrinsic dimension vector. Only they are getting the gradients aligned to reduce the loss required. I mean, only the intrinsic dimension weights are getting the gradients, which will tell them how to align to reduce the loss.
Okay,
You're
so-
just using the projection matrix to get some values, but the actual learning is happening here.
Okay,
The
so at
gradients are not.
sorry.
Yeah.
So at the end of training, the actual weights of model are still being used up in the inference time. Those are not the ones which were used for training the
Yeah.
intrinsic dimension.
Yes.
Right. So that's what is my first question. Okay. So second question is like, if is it true that if I let's say take example of the MNIST classification, right? So if there is a model which is not trained, so there are all weights are completely random. 2 lakh weights are completely random. Now I start training the model, and I just train the intrinsic dimension. So only 750 training only 750 parameters will get 90% accuracy. Is it correct? Completely correct.
Correct.
Okay, so then you said that it is why we are actually using 2 lakh parameters is because convergence is slow.
Faster. Yes.
Right.
Without them, it's slower. Yes.
Exactly.
Yeah.
So here comes my question is like the still even if we are using less dimensions, it is not completely random search through the continuum of that curvature, right? It is guided by the gradients using gradient descent and other optimization algorithms.
Yes.
It is a guided search, and with use of learning rate, we can up to some sort we can increase the learning speed.
Yeah.
But because it is not completely random search, how we are like why it is so slow still?
Why is the training process slow without?
Because it is not a random search that we are going very random directions. It is guided by the gradients. My model really knows what does needs to be updated, right? It is a guided search, so it should not be really slow, right? Theoretically.
No. So if instead of having 2 lakh parameters, if you had only 750 parameters and you tried to train MNIST data, the amount of time you will take to train will be much longer. But if you had additional parameters that are effectively not learning, but acting as dummy parameters, but they are helping you learn faster. If the number of you have to look at the training convergence, how the loss decreases. So if you just use 750, the loss will not decrease steadily. It may just stay flat for a very long time. But if you increase the complexity of the model, your loss will steadily decrease and converge fast. That's the empirical evidence.